Hello. Hello, my name is Sahiti Reddy and my presentation is on Hadoop MapReduce. Hadoop was a concept created by Doug Cutting and was named after his son's stuffed elephant toy. The origins of Hadoop derives from Apache Nutch, which is an open source web search engine, and it was actually originally created in order to support Apache Nutch. In addition, Hadoop was also inspired by Google's MapReduce and Google File System papers. The purpose of Google File System derived from big files and is used to optimize Google's core data storage and usage needs, primarily the search engine, which can generate enormous amounts of data that needs to be retained. Google's MapReduce is a software framework which Google introduced in order to support distributed computing on large data sets on clusters or computers. Google's MapReduce involves two steps, map step and reduce step. There are actually two types of Hadoop installation setups, single node setup and cluster setup. The single node setup allows the user to set up and configure single node Hadoop installation for simple and quick operations. The cluster setup is for multi-node installation and is a bit more complex compared to the single node setup. HDFS. Hadoop provides a distributed file system, HDFS, that can store data across thousands of servers and a means of running work, MapReduce jobs, across those machines running the work near the data. HDFS is written in Java and is formed by clusters of data nodes. In order to communicate, Hadoop file system uses a TCP/IP layer, while clients use RPC, remote procedure call, to communicate. RPC involves an initiation from the client, which then sends a message to the server. The server then responds back to the client, and this process continues going on in the same way. Hadoop file system uses a traditional hierarchical file organization. The HDFS allows the user to move, add, remove, and edit the files in the file system. HDFS is designed to be used on a low-cost hardware and is used for applications with large data sets. The figure here, you can see that there are two types of nodes involved in the Hadoop file system architecture: the data nodes and the name nodes. Data nodes are responsible for serving read and write requests from the file system clients, and name nodes are responsible for executing file system namespace operations like opening, closing, and renaming files and directories. In addition, data nodes perform block creation, deletion, and replication upon instruction from the name node. Both these nodes typically run on machines that run on GNU/Linux operating systems. In addition, since HDFS is built using Java, HDFS can run on any system that supports Java. In addition, the requirement for the HDFS are divided into several categories, which include reliability, scalability, functionality, performance, and perhaps even other categories that may be required later on. The requirements shown below are a few particular scale requirements for the HDFS, which include nodes, which is 10,000, total data, which is 10, number of, which is 100 million, number of concurrent clients, 1,000, Hadoop limits. Although Hadoop also framework has many limitations. One limitation of this framework is that Hadoop is not a substitute for databases. Hadoop does not involve editing of the data SQL that databases use. All Hadoop mainly does is store the data in files. Another limitation is that using MapReduce in many is not always the best algorithm. However, a few solutions are available that may aid in resolving these problems. In addition, another limitation is that this is not exactly the best option in learning Java programming. This framework assumes that you already have basic knowledge in Java before you start using it. Moreover, this framework is also not the best place in learning about networking, error messages, and Unix/Linux system administration, because the framework already assumes that you already have some knowledge in this area. In addition, HDFS is not a POSIX file system, therefore the user cannot assume that decoding will be compatible in both POSIX and HDFS. Hadoop MapReduce engine. Hadoop MapReduce is a programming model and a software framework in which the main importance is to allow for writing applications in a rapidly process vast amount of data in parallel on large clusters of computer nodes. The figure here is an illustration of both MapReduce layer and the Hadoop file system layer. MapReduce is the key algorithm that this Hadoop MapReduce engine uses in order to distribute the tasks around a cluster. The MapReduce consists of two components, map transform and reduce transform. The map transform transforms the input data row of key and value into a list output of key and value. This is illustrated below. And also, the reduce transform takes in all the values and then generates a new short list, which is also illustrated here. An important aspect of the Hadoop MapReduce algorithm is that it runs independently of all other maps and reduces, and therefore the operation can be run in parallel on different keys and lists of data. The MapReduce framework and HDFS run on the same set of nodes, which allows to effectively schedule tasks on nodes where data is already present, resulting in a very high aggregate bandwidth across the cluster. Each cluster on this MapReduce framework consists of a single master job tracker and a single slave task tracker, which can be viewed in the previous image. The job tracker is then responsible for scheduling and monitoring jobs and re-executing those tasks that have failed. The task tracker is responsible in fulfilling the tasks of the job tracker. MapReduce applications do not require to be written in Java. Hadoop Streaming and Hadoop Pipes are two examples of utilities that can be used to implement MapReduce applications. Hadoop Streaming allows users to implement the application with any executable, while Hadoop Pipes use C++ to implement the application. But there are a few limitations to this. For example, maps and reduces need to be stateless for maximal parallelism. You cannot control the order in which the maps run or reductions. Also, it is inefficient if repeating similar searches, and this inefficiency can be measured in both the CPU time and the power consumed. Also, the reduce operations do not take place till all the map operations are complete. As a result, you do not get any data back until the entire mapping has finished. And also, there is a general assumption that the output of the reduce is smaller than the input to the map. MapReduce Java programming. MapReduce Java programming consists of many components, straightforward in the implementation. The following programs actually work on version 1.0. The main purpose of this program is to count how many times a particular word appears in a data set. We are actually comparing version 1.0 program with version 2.0. WordCount 1.0, version 2.0 actually consists more of the MapReduce components compared to the version 1.0. And here's version 1.0. And this is a sample output that comes out of it. Okay, so when writing a MapReduce Java program, it is important to remember that this framework relies and operates mainly on key value pairs. The input is a set of key value, and output is also a set of key value. In addition, it is important to implement the writable and writable comparable interfaces. Important interfaces in MapReduce include mapper and reducer interfaces, which implement map and reduce methods. The mapper process consists of first passing the job conf for the job via the job configurable.configure method and overrides it to initialize themselves. The framework then calls the map method for each of the key value pair in the input split for that task. Applications can override the closable.close method to form any cleanup. Output pairs do not need to be identical to input pairs. The output collector collect method collects output pairs, and also the number of maps for MapReduce is the total size of the inputs. The number of the input size level is usually about 10 to 100 maps per node. The reducer is a set of intermediate values which then share to a smaller set of values. Job conf that set num reduce task method sets the number of reducers per job. The three primary phases of this reducer include shuffle, sort, and reduce. Shuffle phase is responsible for fetching relevant partition from the output of all the mappers using HTTP. Sort groups their inputs by keys. This phase works at the same time as the shuffle phase. The last phase, reduce phase, is a method that calls each pair in the group input. In addition, it seems as though the right number of reduces tends to be either 0.95 or 1.75 multiplied by number of nodes multiplied by map_red task tracker reduce.task.maximum. The value of 0.95 causes reduces to launch immediately. The 1.75 value causes the faster nodes to finish their first round of reduces and then launch a second wave of reduces, doing a much better job of load balancing. Moreover, increasing number of reduces increase framework overhead but also increases load balancing and lowers cost of failures. Another component is the partitioner, which partitions the key space. Hash partitioner is the default partitioner. Reporter reports the progress, sets the application level, statuses, and updates counters. Job conf represents a map-reduced job configuration. This allows you to describe a map-reduced job Hadoop framework or execution. The job conf is used to specify app combiner, partitioner, reducer, input format, and out format implementations. The task tracker uses a mapper task child process for JVM. The child inherits the environment from the parent task. In addition, the maximum virtual memory of the launch child task can be specified using users or admins. Moreover, the localized job directory has the following directories: a job-specific shared directory, a jars directory, a job.xml file, and a task ID. Primary interface in which user job interacts with the job tracker is the job client. The client is responsible in order to facilitate actions in submitting jobs, tracking their progress, access component, tasks, reports, and log. This process involves the following steps: checking the input and output specifications of the job, computing the input split values of the job, setting up the requisite accounting information for the distributed cache of the job, copying the job jar and configuration to the map-reduced system directory, submitting the job to the job tracker, and optionally monitoring its status. Moreover, in order to control the job, it is best to chain map-reduced jobs to accomplish complex tasks, since it is not possible through single map-reduced jobs. In addition, the input format describes input specifications for a map-reduced job. The map-reduced framework relies on the input format of the job to validate the input specification of the job, split up the input files, provide the record reader implementation used to glean input records from the logical input split for processing by the mapper. The default for the input format is text input format. Other components of the job input include the input split and the record reader. The output specification for a map-reduced job is described by the output format. The map-reduced framework relies on the output format of the job to validate the output specification and also to provide the record writer implementation used to write the output files of the job. Output files are stored in a file system. In addition, the default of this output format is the text output format. And moreover, there are other useful features of map-reduce include counters, distributed cache, tool, SLA runner, debugging, job control, data, and data compression. This is actually where version 2. This version improves upon the previous one by using features offered the map-reduce framework. The components, such as demonstrating how applications can access configuration parameters in the configure method. It demonstrates the distributed cache. It uses the tool interface and the generic options parser. And it uses counters. And this is a sample output from the second version, which is pretty similar to the first version. Okay, well, thank you for listening to my presentation, and have a great day.